4-2, day 1, looking at sigma notation and summation notation today. A little bit of area under the curve as well. So in section 4.1, we studied a little bit of anti-differentiation. We worked on the that's not a good color, antiderivative of x cubed dx. And remember how we added a power and divided by a power. Well, this was just kind of the introduction to integral calculus. And we're going to continue on this path, but we take a little bit of a detour here for a bit, and we're going to talk about how could we possibly get the area under some irregular shaped plane region. And so discovering that will help lead us into this large idea of the fundamental theorem of calculus, which is extremely important, and will come in about section 4.4 for us. So today, a little bit of review about sigma notation. I know you've done some of it. This sigma symbol is a capital Greek letter, and it's capital sigma. There's also lowercase sigma, so this one here is lowercase. Lowercase sigma is used often in statistics to represent standard deviation. And the capital sigma that we're going to use is all about summation. So the sum of terms, if I look at this notation right here, there's a few things I want you to be aware of. And one of them is this upper number is really our upper bound. The lower number, of course, is going to be the lower bound. This variable here is what we refer to as the index. So our index of this summation. Now, the a sub I, this would be what we would refer to as the rule of the series. How do I generate my series? Well, a series is a summation of many terms. So I've got a sub I sitting there. The first time this, whoa, that's kind of interesting. This I equals 1 is a counter of sorts. It will count up until we reach the n, the upper bound. And that'll tell me how many terms I'm going to have in my summation, okay? And then the way that these terms are formed is going to be by the rule of the series. It'll make more sense as we do it. The lower bound, the only restriction on the lower bound is that the lower bound must be less than the upper bound. Okay, but it doesn't necessarily have to be 1, it just has to be lower. Typical letters used for the index are I, J, and K, and all this amounts to is that we're going to be summing things up. So let's do an expansion and show you how this summation notation works. I talked to you about the fact that this index is a counter, and basically it's going to be the counting numbers, in this case starting with 1. So the first time through I have my I being 1. That means I'm going to be generating my I sub, or A sub first term to this summation. And if I is 1, well, this rule says well, it's just I, so that becomes a 1. Added with, now I'm going to pick up my A sub 2. My index is going to count up by 1 and become my second term. And when I is 2, well, then that means I'm just plugging in a 2. And so forth. I'm going to count 1 more up. I'm looking at my third term here, which will be plug in a 3 for that I. Okay, then I'm got a 3 going, and so forth. So I'm on A sub 4, which would be add 4. My A sub 5th term in this case, well, then I is 5, so add a 5. My A sub 6th term, now my I turn to a 6. And that is when I'm done, because the upper bound said work until your I's progressed to 6, and then that is the end of your term. So I knew this series would have 6 terms, starting at 1, moving up to A sub 6. We talked about this being a summation, so we could quickly add this together. You can add it in any way you want, but one thing that I think is kind of interesting, especially on this particular series, is how each of these groupings that I just created create the number 7. So really I could say, well, this is going to be 3 times 7, or 21, that adds to 21. Of course, there's many other ways you could add it, but I think that's kind of an interesting one. Letter B, well, our index is K. It says start at 1, let K be 1. So in my mind, I'm substituting 1 in for K. I get 2 times 1 is 2, plus 1 is a 3. Next time through, we are let k be 2. So we plug in 2 and we get 2 times 2 is 4. And I'm adding 1 to 4, so I pick up 5. Next time through, we are on a counter of being 3. 3 times 2 is 6. 6 plus 1 is 7. So I pick up 7. And we do this until now next time is 4. So 2, 8 plus 1 is 9. You can probably see that this looks like it's resulting in the odd numbers, which it is. Finally, put in 5. We're going to stop at our upper bound of 5. And that gives us 11, resulting in 5 terms there. Add them up. If you want, you could say, oh, I'm making 14. 14, there's 28. 28 plus 7, 35. Next, I want to take you and work backwards. Given this series, and a series is any time when we have terms added, subtracted together. Versus a sequence, that's where I was going. A sequence, you've heard the terms series and sequence, and they are not necessarily interchangeable. They do mean different things. A sequence is just a listing of terms, okay? Whereas a series does the summing. So we're working on series here. And I can rewrite this into a nice summation. And things that I notice are the same. I see this 1 over 3. And then I notice things that are changing there, the 1, 2, 3, all the way up to 9. So that gives me an insight. I have 1/3 times a variable. This thing is changing. I'm going to make k my index. So this will be 1/3, 3 times k underneath, right? So that I can get the 1, 2, 3, all the way up to 9. Well, this also helps me figure out if I start my index at 1, it looks like I should be able to finish at 9, and that would result in that very last term. Next one, looking this one over, where are the changes occurring? That number seems to be changing. Everything else in each of these terms, it seems to be staying the same, right? A 5 over something eighths plus 3. So we could write our summation on this. Let's use J this time. J, just for fun. If I started at 1, then this could simply be written as a J, right? So let's start J at 1. Looks like our J is going to finish when we reach 8. And the rule of this series is going to be 5 J over 8 plus a 3. And we could enclose all that so it's very obvious that this is the summation of both of those terms. Sometimes adding them can be a little bit trickier, especially here where I can see I'm going to get an I squared and times an I. This can be I cubed. The numbers can start getting quite large, and adding them can be kind of cumbersome. The other thing that could happen is rather than having a nice series going from 1 to 5, maybe it's a 1 to 50. Ooh, I really don't want to list out 50 terms so that I can add them up. So there are some summation formulas that can help us out. People have recognized patterns to the summation, and we can use these shortcuts. So you'll notice shortcut number 1 is when we have a C, which is a constant. So this would be like, okay, what if I have the summation of 5? And maybe it's going up to 3, from 1 to 3. Well, that would result in 5 plus 5 plus 5, right? First term, second term, third term. That's simply 3 5s. So notice how this is going to be. What was your constant multiplied by the number of times it got repeated? So simple multiplication there. Remember, that's assuming that our index started at 1. This one over here, what if I had just the variable like we had done on our very first problem where we had just I there and we summed them up. So it was just the counting numbers that we were summing. Well, there's a nice quick formula for that as well. Whoops, where are we going here? The quick formula says take n, which is my top number, right? Take n and multiply it by n plus 1. And then that'll work. So that's kind of interesting. N plus 1. Where was that beginning? Oh, now I'm too far back. I'm looking for this one. We were making sevens. Remember how I pointed out we were making 7? And this new rule says it's n plus 1. Those multiplied, the product of those two values, and then divide by 2. It's a little bit different than what we did, but look what's next in the series. So this is saying n was was 6, and n plus 1 is 7. So I take 6 times 7, the one right next door to it. That would give me 42. 42 divided by 1 gives me 21. Interesting. But isn't it true that 1 plus 6 kind of generated that next number, didn't it? And 2 and 5 made 7, and 3 and 4 made 7. Not just a coincidence, but very interesting, allows us to write that formula. So you can kind of see how that formula was built by looking at that example. Again, here's n squared, n cubed formulas. You can apply formulas. There are also some properties revolved around summations. Of course, there's always properties, right? This one says, what if I have some multiplier times the series rule? Well, then it would be true that we could do no harm by just pulling that multiplier out front, summing up the series based on the rule, and then coming back and multiplying it by that k afterwards. This would be an example of that situation where I have the summation of j equals 1 to 4 of 5j. Well, I could say that this is going to be equivalent to 5 times whatever the sum of j from 1 to 4 was. Okay, there's that rule. And then addition, subtraction, you see it as two different rules, I believe, on your note sheet. If I have two different rules of a series, kind of like this one, then I can break them up into individual ones, so I could have a summation going on just of 3, and I could sum up the 5j. Maybe it's easier to do it by hand if I break things down. And so these rules show you that that is true. What you'll notice is not true is, oh, let's take this rule out here, is a multiplication one that says you can sum these up individually if they're multiplying, and then multiply the results. That is not a property. Notice it's not listed there. Matter of fact, it would not work because each time here I've got a specific number times another specific number. And that number's constantly changing. I can't just simply take the product of all these i's and then multiply it by the product of the other i's. You will not get the same number. So no rule for the product of them. All right, how do we approach A? Well, the simplest way is to do the summation with subtraction and addition rule. So let's break this up into two separate summations. We know that's a legal move. We've got a property for it. And then, even to make it one step simpler, I think I'll use this multiplying rule that says, oh, hey, you can bring k out front. So I could bring this 5 out front and place it out front. So I think I'll use that rule as well. So I have 5 summation j equals 1 to 4, I'm sorry, yeah, of j minus the summation of j to 1 to 4 of 3. Now, I want these quick rules up here. So I'll bring that down where we can see them as we work. First one, I have a variable that follows this rule. So it's an n plus 1. What is n, you might ask? Well, n is defined right on the top of our summation. So my n in this case is 4, isn't it? So I'm going to have 5. And then here's the rule for the summation formulas. It'll be n, which is 4, times n plus 1, which would be 4 plus 1, or 5, divided by the 2. We just followed that. Minus, now I'm going to go into my second summation. I have a constant here, so I'm going to use the constant formula, this guy, which simply says you're going to take your constant, my constant is 3, and multiply it by n. Well, once again, my n was 4, so 3 times 4. And then now let's just simplify. We'd have 4 times 5 is 20, divided by 2 minus 12. And 2 goes into 20 10 times, so we're looking at 50 minus 12. Oh, that gets me 38. And these are all equivalent, so I can write equal signs. Would it have been a lot of work to simply expand our sum by plugging in 4? No, not really, wouldn't it? Why would I start at 4? Start at 1, I would have had a 2, put in 2, I would have had 10, I would have had a 7, and so on. I would have had 4 terms, add them up. But just to get some play time with these formulas is what we're after. For B, I don't see anything that has like a variable minus a number. I don't see that rule sitting here anywhere. So how could I break this particular summation down so that I could use my rules? You're right. Let's just expand this. Let's FOIL this baby out. Let's distribute stuff, and we will get 3 terms now, won't we? We'll have a k squared, a minus 4k, and a plus 2 by expansion. Now I'm going to use 3 different rules. I'm going to use the squaring rule, which is down here. I'm going to use the k rule, which is right there, and then the constant rule, which is over there. So I'll be using in the order of, oh, it looks like 3, 2, 1, doesn't it? All right. Let's expand this. So I'm thinking of each one separately, right? Summation of each one of those individually. And so I've got a k squared. My n in this case, right, is 8. I've got an 8 sitting up here. So I'm going to have 8, 8, 8 going in there. That's going to give me 8, 8 plus 1, and a 2 times 8 plus 1 over 6. Subtract 4, I'll pull away. Let's look at just k. That's this rule. Remember, I had 8 for my n, so I'm looking at 8 times 8 plus 1 divided by 2. And our last is the constant of 2, so it's a plus sign there, so it's a plus. Now I'm working with the constant rule. We're traveling to 8, so it's going to be a 2 times 8. 2 times 8. And then it's just going to be math from here on out, a little bit of arithmetic. 8 times 9 times 16, 17 over 6 minus 9 times 8. I could take 2 into 4, couldn't I? So 2 times 8 times 9 is 72. I'll come back in a minute and update again. And lastly, we'd have 16. 9 times 8 is 72, so I'd have 72 times 17, but 6 goes into 17. I'm into 72 12 times. Now I've got to do 12 times 7. I'm going to break that up and think of it this way. So 17 times 10 is 170. 17 times 2 is 34. I'm getting 204. Double 72, we're talking 144 plus a 16. See, these actually, come out pretty decently here. 204 minus 144, I can do that in my head pretty easily. That's 60 plus 16 equals 76. I'll go with that. I feel like that's the wrong number, though, just from working it in class yesterday. Double check my math on that, guys, but I kind of feel like there might be an error in there. Oh, hey, let's double check it because I wanted to show you how to use your calculator on this too. So in your calculator, grab your calculator, hit pause if you need to. You can do summations in your calculator, of course. So we'll let the big secret out. I'm going to go with the alpha key and then the window key so that I can grab that F2 function. And there is summation. It's number 2. It's also available under math menu, math, I think option 10. What should I use for my index? Well, I'm just going to use x because it's so convenient to grab x on our calculator. So x equals 1, 2, 8. I'm going to do this b value, or this b problem on here. And then the sum. Okay, now I got to get my rule of the series in. I'm going to put in an extra parenthesis just so I can ensure that when I square this, it maintains, or it gets included in the whole summation process. Okay. 92, okay, that is what I thought the number was. So we are off, Well, I am. And where did I get off? I feel like that first number is correct. 144 sounds correct. And then, oh heavens, maybe you caught this problem, my mistake way back in the beginning. Uh, when I FOIL this, right, we'd have this. I wouldn't get 2 at the end, I'd get 4. Heavens. So there's 4. This becomes 32. I'm so sorry. This becomes 32. This becomes 32. And boom, there's the 92 that the calculator verifies with us. I bet you were wondering when I'd catch that. Glad I did. Okay, last one, B. All we need to do is let's expand this, but let's expand that carefully so I don't make that silly mistake I just did. I'm going to hold off on that first I. Expansion would be I squared minus 6I plus 9, how about? And then I would send the I through, and we'd have a summation from 1 to 5 of I cubed minus 6I squared plus 9I. And we want all that. That's our rule of series there, and we would expand it if we wanted, or we could use our shortcut rules, and this time we would be involving a cubic one as well. And I'm not going to do it for you. I think you understand how to do it. The next thing that we kind of travel into is, well, why are we talking about all the summation? Well, there's a purpose for this. We're talking about summation because we're going to sum things under a curve like this. And so the summation kind of fits in this section so we can know how to sum things. This in the red, it says, we know the origins of calculus are connected to 2 classic problems, the tangent line problem as well as the area problem. This started way back. The ancient Greeks were able to determine formulas of areas of some general regions by an exhaustion method. Well, that just means they kept trying things over and over. Or, like Archimedes did with the circle, trying to find the area of a circle, he started off with thinking of, okay, I know how to find the area of, even one back, the area of a triangle. And so he said, well, a triangle sort of is like a circle, but not really. We have a lot of area that we'd be missing, right? So then he just kept scaling it up and said, well, let's produce then a square, because a square is nothing more than 2 triangles. Oh, well, I can even do better than that. I could create a pentagon, right? That's got 5 triangles to it, and so forth. So eventually, he thought, well, I can even make this more accurate because I could put a pentagon on the outside. Why didn't I use a different color? I could circumscribe a pentagon and inscribe a pentagon. Then I have a lower amount in the inside and an upper value on the outside, and the true value of the circle has to fall somewhere in between the lower and the upper. And if I made enough triangles, I could eventually make this mimic a circle so ever closely. And that is exactly what he did. I think, yeah, here, it said he used 96 sides, a 96-sided polygon to generate a value for pi. So we're talking in like 212 BC, he died, so almost 300, 250 BC-ish, we're coming up with an estimate for pi that fell between 3.1408 and 3.1285. So accurate out to the hundredths position. Pretty impressive. I think another neat invention that Archimedes came up with was the Archimedes screw. They used it for water, to move water from a lower level to an upper level. We still use the auger today, don't we? Well, it's called an auger on a farm. I don't know, grain auger. And manufacturing plants use it to move material from one area to another. And, you know, a lot of conveyor belts are used, but augers are also very efficient. And so, where does that take us? Well, what we're going to do is work on summing areas under curves, okay? Oh, I said this was going to be a right endpoint. So this one would look like, make 5 rectangles out of this space, and I'm doing it very quickly because I can see this video is getting kind of long. And what we're going to do is create 5 rectangles from 0 to 2, and then I can sum each of the areas of the rectangle, because rectangles are simply length times width, right? And we can sum those up. Each of these having some width, some change of x value. And notice I drew mine very carefully so that each of them have 2/5 of a width. So we will go through that. There's going to be called lower and upper sums. Oh, this was right. I just made this left. Consider, let's flip-flop these, okay? Because I just went backwards. Left endpoint on this one. Making an upper sum. I have overage, don't I? So obviously I'm going to be overestimating this. All right, homework following this section is 6 through 10, 14 through 20. Just do the evens on these. If you want to, you can hold off on these. We're going to continue those in class today. Thanks.